Our universe is a vast and enigmatic expanse. It teems with stars, galaxies, and mysterious phenomena. But beneath this cosmic tapestry lies a hidden language written in the very elements that make up everything we know. This is the language of cosmochemistry, a captivating field that seeks to unravel the universe's chemical secrets. Cosmochemistry delves into the origin of elements, the processes that forge them, and their distribution throughout the cosmos. It's about understanding the chemical composition of stars, planets, and the interstellar medium, the diffuse matter that fills the space between stars. By studying these celestial objects and materials, cosmochemists aim to reconstruct the history of our universe. Imagine being able to trace the life cycle of a single atom of carbon, from its fiery birth in the heart of a dying star, to its incorporation into a swirling cloud of gas and dust, and finally, its eventual arrival on Earth, where it becomes a fundamental building block of life. This is the power of cosmochemistry. Through this captivating journey of cosmic proportions, we gain insights not only into the universe's past, but also into our own origins. Cosmochemistry provides us with a unique perspective on our place in the grand scheme of things. It reminds us that we are all made of star stuff. Our universe began with a bang, the Big Bang, a cataclysmic event that brought space and time into existence. In the first fleeting moments after the Big Bang, the universe was an unimaginably hot and dense soup of elementary particles. As the universe rapidly expanded and cooled, the simplest elements, hydrogen and helium, began to form. This process, known as Big Bang nucleosynthesis, laid the foundation for the chemical diversity we observe today. Hydrogen, the most abundant element in the universe, was created in vast quantities. Helium, the second most abundant element, emerged as well. However, the intense heat of the early universe prevented the formation of heavier elements. The universe needed to cool further and become less dense for more complex atomic nuclei to form. This is where stars, the cosmic furnaces, come into play. Stars are massive balls of plasma held together by their own gravity. Deep within their cores, temperatures and pressures reach unimaginable extremes. It is in these stellar cores that hydrogen atoms fuse together to form helium, releasing an immense amount of energy in the process. This nuclear fusion is the engine that powers stars and the source of their brilliant light. As stars age, they continue to fuse hydrogen into helium in their cores. Eventually, the hydrogen fuel in the core begins to run out. With the outward pressure from nuclear fusion dwindling, the core contracts under its own gravity, causing temperatures and pressures to soar even higher. In these extreme conditions, helium atoms themselves begin to fuse, creating heavier elements like carbon, oxygen, and neon. This process, known as stellar nucleosynthesis, is responsible for the creation of elements heavier than helium. For massive stars, this stellar alchemy continues, forging progressively heavier elements in their cores. Carbon fuses into neon, neon into oxygen, and so on, until iron is produced. The formation of iron marks a turning point in a star's life. Unlike the fusion of lighter elements, the fusion of iron does not release energy. Instead, it requires energy, making it an energetically unfavorable process. When a massive star develops an iron core, it has reached the end of its life. The core collapses under its own gravity, triggering a catastrophic explosion known as a supernova. The death throes of stars, while cataclysmic, are essential for the creation of new celestial bodies. Supernova explosions scatter the heavy elements forged in stellar cores into the interstellar medium. These elements enrich the surrounding gas and dust, providing the raw materials for the next generation of stars and planetary systems. Our own solar system formed from such an enriched cloud of gas and dust, known as the solar nebula. About 4.6 billion years ago, this nebula began to collapse under its own gravity. As the cloud contracted, it began to spin faster, and the material within it flattened into a rotating disk. At the center of this swirling disk, gravity pulled in more and more material, eventually forming the protostar that would become our Sun. The remaining gas and dust in the disk continued to orbit the protostar, colliding and sticking together over millions of years. These collisions led to the formation of larger and larger objects, from dust grains to pebbles to planetesimals and eventually to the planets we know today. This process of planetary formation is a remarkable testament to the power of gravity and the intricate interplay of matter over vast stretches of time. Section 5. Meteorites, time capsules from the early solar system. To piece together the history of our solar system, cosmochemists turn to meteorites, fragments of asteroids and other celestial bodies that have fallen to Earth. These cosmic messengers provide invaluable insights into the conditions that prevailed during the early solar system's formation. Meteorites are like time capsules, preserving pristine samples of the materials that made up the solar nebula. By analyzing their chemical composition, isotopic ratios, and mineralogy, cosmochemists can glean information about the processes that shaped our solar system's evolution. Some meteorites, known as chondrites, are particularly intriguing. These primitive meteorites are thought to represent the building blocks of planets. Chondrites contain chondrules, tiny spherical grains that formed in the solar nebula's hot, turbulent environment. By studying the composition of chondrules, cosmochemists can learn about the conditions that existed in the solar nebula before planets formed. These tiny grains provide a window into the earliest stages of our solar system's history. Section 6. Planetary differentiation unraveling Earth's layers. As planets formed, they underwent a process called differentiation, where denser materials sank towards the center, while lighter materials rose to the surface. This process led to the formation of distinct layers within planets, such as Earth's core, mantle, and crust. Cosmochemists study the composition of these planetary layers to understand the processes that drive differentiation. By analyzing volcanic rocks, which originate from Earth's mantle, they can infer the composition of Earth's interior. Seismic waves, generated by earthquakes, also provide valuable information about Earth's internal structure. By studying how these waves travel through different layers, geophysicists can map out the boundaries between Earth's core, mantle, and crust. Understanding planetary differentiation is crucial for understanding a planet's evolution, including its potential for harboring life. Earth's differentiated structure, with its molten iron core generating a protective magnetic field, has played a vital role in making our planet habitable. Section 7. Stardust Whispers, Unlocking Secrets of the Early Solar System. Interstellar dust particles, known as stardust, are another valuable source of information for cosmochemists. These tiny grains, typically only a few nanometers to micrometers in size, condense in the outflows of dying stars and supernova explosions. Stardust grains preserve the unique isotopic signatures of their stellar origins, providing a fingerprint of the stars that enriched the early solar system. By analyzing the isotopic composition of stardust grains found in meteorites, cosmochemists can trace the origins of our solar system's building blocks. These tiny grains also offer clues about the processes that occurred in the interstellar medium before the solar system formed. Their composition reflects the chemical evolution of the galaxy, providing a glimpse into the conditions that existed billions of years ago. Studying stardust is challenging due to their minuscule size and rarity. However, advancements in analytical techniques have allowed cosmochemists to unlock the secrets held within these tiny cosmic time capsules. Section 8. The Chemistry of Life, Seeking Our Cosmic Origins. One of the most profound questions that cosmochemistry seeks to answer is how life emerged on Earth and potentially elsewhere in the universe. Organic molecules, the building blocks of life as we know it, are found not only on Earth, but also in meteorites and the interstellar medium. The presence of organic molecules in extraterrestrial environments suggests that the chemical precursors to life may be widespread in the cosmos. Cosmochemists study the composition and distribution of these molecules to understand the conditions under which they form and the potential for life's origination on other worlds. One intriguing finding is the presence of amino acids, the building blocks of proteins, in meteorites. This discovery suggests that the raw materials for life could have been delivered to early Earth from space. While the origin of life remains one of science's greatest mysteries, cosmochemistry provides valuable clues about the chemical inventory available for life's emergence and the potential for life beyond Earth.
If you enjoyed this video, don't forget to like, share and subscribe for more fascinating insights into space exploration and astrobiology, and be sure to let us know in the comments which planet you think is the most promising for future human habitation. Until next time, keep looking up, keep asking questions, and never stop exploring the wonders of the cosmos. The universe is waiting to be discovered.